Okay, that's going to be the most difficult part of my presentation. I'm just so hey everyone, my name is Eleftherios. You can call me Elef, much simpler. I'm originally from Greece. I moved to Berlin back in 2011 to work for SoundCloud, a music company. Back then it was a tiny company. I joined them early and then stayed with them for 6.5 years. And at SoundCloud I was leading all their data science teams and their data engineering teams. At SoundCloud that was machine learning on the one side, data analytics on the other side, music information retrieval, this pretty much extracting signals extracting information from music signals, and then data engineering on infrastructure building. So I have a background in statistics and applied math. At some point I started a PhD here in Berlin that I dropped out a year later because I got promoted at SoundCloud, so I was like, I guess I should continue on the industry. And then back in 2017, together with my friend Alexi, that you're going to meet next week. Yes, okay, you're going to meet Alexi next week. So we ended up starting Monadic. And towards the end of 2016, actually, we both got excited with cryptocurrencies and everything else that was going on there. And then eventually what we set out to do with Monadic was basically, we had this different vision for code collaboration and value exchange in open source communities. So we're working on this project that is called Radical. Maybe you heard about this. So Radical is a secure peer-to-peer network for code collaboration. At this current state it's using IPFS, which is this decentralized storage technology. And then on top of this we're building an economy for coders pretty much. We want to help developers monetize their work while also contributing to the commons, basically in the open, free software. So it's quite a lot to go, and we've been we've been working on this for the last 2 years, and now we have a lot of lovely people around us, which is great, including Emma, Angie, and Abby that are in the room right now. And and what I'm doing on the project, focusing on a lot of different things, but primarily I do research on mechanism design and economics. Like my day-to-day looks a lot like basically coming up with mechanisms, coming up with systems, and then try to reason about them, and then try to break them, which is the most fun part, by the way. So you try to find holes in your own thinking, and then eventually simulating a lot of that and try to reason more mathematically and with more evidence about that. That's one part of it. I do a lot of other small things, but I guess they're not that interesting for that group. Today we will be talking about mechanism design. Please stop me wherever you want. Let's make this interactive because there's a lot of content. It is already a challenging thing to try to basically capture, the field of mechanism design in 2 hours. But please make it interactive. There are no stupid questions. Like please, if you don't understand something, bring it up and let's make the conversation. Also on my side, I don't want to be talking for 2 hours, so it will be much more nice for both sides.
Also, it would be helpful if you stop at certain points to ask if anybody is on the same page or not. I think that will be helpful for
a great practice. That sounds great, actually. Cool. Okay. Then let's zoom in on the topic. So the objectives of the day. As I mentioned, this is an introduction to mechanism design. So I wanted to be pragmatic. I thought about the following 5 objectives. So I want you to understand, when you leave the room today, to have a good understanding of what mechanism design is. If someone asks you on the street, you should be able to say, this is what mechanism design, the science of mechanism design is about. So that's the first objective. The second one, which I think is the most interesting one, is I want to show you a bunch of real applications of where this thing is being used, and talk a little bit about how the designers and the actors in some of these situations actually behave. The third thing is basically give you a bunch of basic starting points to, if you're interested in the field, to be able to start your journey from somewhere. The fourth one is describe the intersection between mechanism design and crypto-economic peer-to-peer systems. As this is a program for specifically for the decentralized space, I thought that it might be interesting to try to bring some of the theory and the applications we see from the rest of the world to to some of the applications that you see on the peer-to-peer / blockchain space. And then finally, I have a bunch of resources, only for the ones of you that are interested, and honestly, like, not everyone has to be interested on the topic. If you want to continue your journey, like, I can point you to a bunch of different places, so you continue your research. How does that sound? Okay, great. Market design is a branch of game theory, so I thought it might be a good idea to actually start with a game. So let's watch this video. You cannot see it there. Yeah, unfortunately, this is our browser doesn't support it.
Oh, not here. Germany needs my computer. Let me get
You can also get the better collection.
I do, but
Actually, I think I can show you that with the. It's a browser program, actually. Great. Excellent. Yeah, okay, we got it. We have sound. Yeah, same problem, okay. Let's do this. Let's do this again.
They're certainly faults. Yes, it's okay to buy a course. They're certainly fault after fault. They're just hitting the ball straight in the net. Sorry, it's blinding the obvious what's going on. You've got the referee out on court. It's a doubles match in China and Korea. They seem to be serving service faults quite deliberately. It's as if neither player wants to win the match. There's a simple answer. Tell both players, if you don't play properly, you're both thrown out of the tournament. They're both trying to lose, and that is unforgivable. This is the Olympic Games. They owe a duty. This is what all athletes swear to, that they will comply with the Olympic code of conduct, and they should be warned quite specifically that either they play properly or they will both be disqualified from this tournament. The referee is out there.
He's actually got a black card in his hand.
So, does any of you have an idea about what's going on here?
They can't even start the game, or what?
No, they try to lose. They try to play bad. I thought about it because I think there was the next team would be someone who's really strong, or it was about the system. They wanted to control which team they can battle next, I think.
That's right, you're spot on actually. That's exactly what's going on. So what's the story here? So this is the Olympics of 2012 in London. Let me go back to my presentation. So this is the Olympics of 2012 in London, and what has happened here is that basically this is the competition for badminton, right? And this is basically as important as it gets in the sport, right? And there are a few teams that actually have managed to make it to the Olympics, and the system, the way that the system is organized there, it starts with what we call round robin. So you basically have 4 groups of 4 teams, okay? And then from each of these groups, the top 2 teams, each team plays with the other teams in the group, the other 3 teams in the group. And then from each of these groups, basically the top 2 teams advance, and then they start they move into a knockout phase where they meet other teams from the other groups. Okay? So what has happened here is basically a day before there was this massive surprise. So there's this one team that everyone understands as the best team in the world, the Chinese team actually, and a Danish team actually has managed to win against them. So what's going on really is that now the Chinese team, which is the one that everyone expects to win, is now second in the group. It still qualifies, and the Danish team is first. And this is basically the teams on the other group, and both of these teams have already qualified, so they know that they advance into the next round, but actually they both try to avoid the good team that's now second. Right? So what's going on really here is that they both try to lose, and if you spend a little bit of time on the topic on the internet, it's fascinating. You see, like really, like it's very, very funny. You see the whole game. It's a piece of art actually. Both teams trying to lose at the same time. Right? So I recommend that. I've never seen anything like that. I've seen similar cases, for example, on football, on soccer, you'd say. And on basketball sometimes, but nothing so outright obvious. So what you're observing here is pretty much a failure in rule setting, right? So if you really think about what's going on here, is that someone was designing a system, which is the tournament designer, right? And actually, it seems that they haven't thought that well about their own objectives. Right? So a system and the rules of the system need ideally to lead to positive objectives, right? And it seems that someone actually has forgotten to do their work. So the obvious point that I'm trying to make here is like the way you design a system, when you design a system, the rules of the game matter, right? This sounds like very, very obvious. Now, moving towards mechanism design and what really mechanism design is, one intuitive way for me to think about this is the following. So I mentioned before game theory. So game theory is basically the science of how to behave in games, right? So what's the best way for you to play a game? What's the outcome of strategic interaction between actors in a given game? So that's game theory, which is the one side of the coin. Now mechanism design is the other side of that coin, which is basically how do you design the actual game, you being the designer, to ideally lead to some kind of positive outcome. Try to reason what happened with the badminton case. Obviously, let's think about the actors for a second, right? So in the badminton case, we have a bunch of teams that compete, and in the Olympics, pretty much every team, the objective that has is to win a medal. Usually if you win a medal, then that's already a big success. So that's quite clear. But on the other side, you have the tournament designer. And the tournament designer has a bunch of different goals, I would say, but can you think of some goals that they might have? What do you think? If you were designing the badminton the badminton competition, what would be your objective? How at the end of the day you would know you were successful?
Clear outcomes of the games.
Okay, sounds good.
Right. Audience engagement.
That's right.
Yeah.
A winner and a loser?
As simple as that, right?
Best teams play the longest and worst teams play the shortest.
Great. All of these are actually correct answers. And we can take it even further, and you can think about, for example, revenue maximization. Right? Like potentially the tournament designer wants to sell tickets, and because they want to sell tickets, they want all of these things that you all mentioned. That they want actually competition, real competition, and they want great games, and they want satisfied customers, and they want the advancement of the sport, right? Like you can take it in many different directions, but these are all of the objectives that the tournament designer has, and it seems that they actually had not thought well about that. So first, an important slide is like think about mechanism design versus game theory. Two sides of the same coin, right? So the one is basically assume a game. How do I accomplish my objective as an agent in the game? While the other one, mechanism design specifically, how can we design a game? In this case, the game was a tournament. How can we design a tournament that leads collectively to the objectives that we all want? Is that clear? Great. Okay, I see other cases. Excellent. So you might already be asking, like, okay, what's a game really? So a good way to think about this, think of a game as a situation where we have a set of actors which are both autonomous and strategic. And autonomous and strategic, like think of it as they all pursuing their own objectives. You can even add selfish objectives if you want. But despite their strategic behavior, we want to make sure that the whole system is functioning well. Okay? So yes, so let's reason a bit about what we observe, and this is almost like what we do with every design, with every system that we have. Like at first, it's such a simple exercise. We start with the following. We try to spend a little bit of time and try to understand. Okay, like let's be explicit. Let's try to understand each of the different actors in that game, right? We mentioned before teams and the determined designer, but actually you can take it even further, right? You can imagine the referees, which you saw in the video. So what happened actually in that video was that the referee eventually said like enough, and they banned the one side, and they were like you're out, and he stopped the game. So the referee is another actor in that game. The spectators, like the visitors, are also actors, right? So the first part of the exercise is always like try to understand who are these different actors and what kind of role are they playing in that system that you design. And then the second part is you try to start reasoning about what are their objectives, what are they really trying to accomplish in that game. The third one, which is actually a very, very important one, is in different systems, different actors have different informations, and we're going to see a bunch of real examples here. Funny enough, even in the situation that you saw in badminton, it seems that some of these teams have different information. And what I mean by that is that the team that eventually got banned, they seem to operate on the hypothesis that they can continue to play the way they were playing, and they thought that they're not going to be banned, right? Because they thought that basically this is up to them to figure out if they want to do that, right? So even that is a case where basically you see that different agents operate under different pieces of information in a sense, and that's another thing that you want to think about. Fourth component is that each of these agents actually usually are pursuing a set of actions or strategies, and you can think of the one as basically like break down a strategy into a set of actions, and we will see very concrete examples later. And then finally, each of them have an outcome. Usually they get something from that game, right? So these are the 5 components that usually, when we start with the mechanism, we try to go through this quite quickly, and we try to spend with the team a bit of time, try to reason about them. And by simply doing your due diligence here and like starting to reason about that, you already go far. You simply by following simple logic, you will start observing different holes that you might have. On the flip side, also somewhere in there, you also have uncertainty. In each of these categories, you actually might have uncertainty, and very quickly you might realize that like, this is a hole that you might really struggle to fill. It might not be so easy. The one case that I just mentioned is this asymmetry in information that many times you have within a game. So mechanism design is pretty much the science that helps us reason about all of these things, right? Again, imagine a system of n agents. We have a set of possible alternatives x. Each agent has some sort of private information that we try to model, and usually the way that we go about objectives, we try to reason about utility maximization, and you will see on a bunch of cryptoeconomic systems many times this will default to money, but it doesn't have to. Right, so mechanism design actually can go beyond financial incentives. You can take the same science and try to abstract that and try to reason about other type of incentives that certain of your actors might have in a system. And the funny thing is that games are everywhere, right? So we started with actually a sports game. We started talking a little bit about game theory and mechanism design. We started defining what a game is now. If you think about what satisfies the definition that we gave before about a game, you will really find very diverse and fascinating examples. Some of the examples that we're going to talk about today, we're actually going to study an auction. We're going to talk about how auctions work, where someone's selling a good and a bunch of other actors actually are bidding to buy that. That's mechanism design. And another funny story about that is that 95% of the revenue on the internet right now comes through auctions, right? Think about internet advertising and all of that, which is interesting and problematic in its own way, but I'm not going to go there today. So that's one use case. Another use case that actually we were just discussing before is the use case of matching. Imagine that you have a set of students that apply for universities. How do you go about designing such a system to have a job tomorrow, to have the best performance as you wish? Or think about hospitals and patients, right? So these are all different systems that someone is actually doing this type of work and tries to reason about what is our collective, what's the outcome that collectively we want to see with this game? How can we engineer different incentives left and right to make sure that this is satisfied? What else? Obviously, we have a lot of cases on computer networks, how the internet infrastructure that you all use behind the scenes. Also, that internet, like data routing, involves a lot of game theory actually, and a lot of mechanical design. So you see applications everywhere. I think that's one of the things that I feel very certain is that after the session, you will start seeing some of these games actually being played around you, and you will be aware of them in a sense. Any questions? All on the same page until now. Okay. As you observe, I try to basically avoid math, and I will try to avoid like as possible math. As I think some of you have different levels of that, right? So I'll try to keep it much more conceptual and give you more practical tools on how to navigate it. Yes.
How much importance is put on those notations? So you also like no importance. So we don't need to
very little, exactly
remember
like
the notation.
Absolutely right. Like I use the notation because many times that's how I think about it, and it's sometimes helpful. In one of the exercises we're going to use notation, and then I'll tell you to actually take it more seriously. But for now, don't stress about the notation. Okay. Cool. Any other questions? Great. Okay. So games and mechanisms everywhere. Collective choice are usually made indirectly through institutions in which agents interact. So the mechanism basically is simply the formal representation of that institution in a sense. If you want to think about it like that. And usually we have a strategy for each of these different agents that we talked about, and we have a bunch of outcomes. You see a bunch more examples here. Like auctions will come up a lot. But also, like, for example, you see elections there, right? Like, this is, again, another case where someone is really designing a system, hopefully, about how to engineer the best possible outcomes. You see a lot of mechanism design in policy, for example, like how to set public policy. This is the same story. It's the science of rule setting, right? So wherever you see rules, hopefully someone actually at least has done their diligence. And one interesting concept that actually has been helpful to me quite early on to try to understand how to reason about that is this concept of price of anarchy. So this is a concept that comes from computer science, and this is one of the major contributions of computer science brought to a field that primarily has been economics for the longest period of time. So the whole story with price of anarchy goes like this. We have a lot of paradoxes where we can quite easily prove that selfish behavior doesn't always lead to good outcomes. I think probably that's intuitive with everyone, right? So depending on where you stand in your politics, you probably you will be understanding that. That's actually the case most of the times, right? So most of the times, the moment you have a bunch of agents that they're all pursuing their own selfish objectives, usually that makes things actually really, really hard. So the concept of price of anarchy is the following. Assume that you were designing a system where you want your agents to pursue different actions. And now for a moment, assume that you were actually the dictator of the system. Okay, you were the person that actually can go and dictate every single action for any single agent within that system. Okay, and basically now try to reason about the steady state. Like when designing a game, assume that everything is going as you expected, as you want it to be. Like basically try to reason about how well your system is performing, right? So that's what we call in economics, this steady state we call equilibrium, like that's Nash equilibrium, you might hear that left and right. A very simple explanation for that is basically it's a steady state of a system. Every agent is pursuing their actions. At some point, we actually all of these different behaviors converge to a steady state. That's an equilibrium. So now the price of anarchy says that basically take the system, like imagine that everything was going as you wanted, you the designer, you wanted that system to look like, and then this is your best equilibrium pretty much. That's the best steady state that you can have. And now try to basically use game theory and try to remove this assumption and let basically players play in their own selfish way and try to reason about the worst steady state that the system can have, right? And pretty much like the price of anarchy is the ratio between the two, about your worst possible steady state versus the best possible steady states. Good mechanisms usually get this number to be to 1. Ideally, you want your worst steady state to be your best one, right? Like ideally, you came that close to the best steady state. And while this sounds subtle, like, and I don't know if already intuitively saying like, oh, this is a major contribution. I think what computer scientists really added with this concept was they really quantified that concept. Previously in economics, it was much more theoretical about, okay, what's a system and let's see how far we can go with it, what's best or optimal performance, right? So many times actually already that is really hard to reason. But basically computer science, by adding this concept of price of anarchy, they gave a very practical way for scientists to actually be able to reason about the behavior of a system. Any questions on that? Yes.
So what is being used in a ratio? What is is it like a max, as a society as a total, basically utility surplus things, or
right,
what is the?
I mean, it depends. The answer is depends on the game, right? It depends on the system that you're designing. So in a lot of systems, as we're going to see later, we're talking a lot about this concept of social surplus, which is very simply, to avoid technical terms, basically imagine each game, each agent has a utility function. Basically, all of you, you're participating in the AccessP2P program, and probably your objective is to learn as much as possible about centralized systems, right? So if we were able to quantify that and then sum all of your different utilities, then that would be the social surplus of a system. So basically the utility function that the sum of the utility function that each agent has. Yes. Now obviously what's a utility function for each system is it varies on the system, right? It very much depends on the system that we're actually trying to design. I wanted you to get a bit of a feel of the space. Let's actually move to a more real scenario. So I bet that most of you know eBay. Has many of you participated on an auction in eBay? Yes? Okay, so did you win?
No.
And none of you won? You won?
I think I won once.
Yes?
Maybe.
Okay, so do you remember, like, can you tell us a few words about it? Like, what was the good if you want to? And
I mean, I was young, and I think I was trying to find like a certain pair of shorts. Something.
okay,
They were on eBay.
okay,
And I ended up like bidding for it, but I had no idea what to do. I think it was right above the starting bid or something. And then someone else bid, and then I bid, and I kept going for it, but I kept just incrementing. I was like really young, I shouldn't have been on eBay. I was kind of like really scared about it. And then like finally I won. I've done a lot of auctions on Neopets.
okay.
You know Neopets, right? That old pet game online.
Okay,
Same process of.
okay. Thank you.
You're welcome.
Do you remember what you paid? And I don't mean like what was the price for the good, but what you actually paid yourself.
What I
Versus-
actually paid?
Meaning that you bid something, was that what you paid?
I think I ended up paying more because I had to like transaction costs or something. I don't know. Like whatever it started at, I paid like more, like $15 more, and then I ended up paying more. Does that make sense? No?
I'm not sure.
Okay, this could be. I don't know.
Okay, thank you. Okay, for the ones of you that actually haven't participated on an auction on eBay, eBay is providing this platform for goods right? Like basically allows sellers and buyers to interact. And they have this auction feature where you can basically say, I want to sell my good, and then let the market figure out the right price for that. Now, a lot of us, many times when we think about auctions, we default into what we call in mechanics design first price auctions. And first price auctions are actually auctions where the winner is the person that actually bids the most, right? So the person that bids the most is the winner, and the price that the winner pays is their bid, whatever they bid. Now, eBay actually, for many years, the mechanism that they were following wasn't that. So on eBay, basically, what you would follow is what we call a second price auction. And a second price auction basically pretty much says that, like, let all people bid for a good, and when eventually we have the winner, the person with the highest bid wins, but what they pay is the second biggest price. Okay, I know that sounds like not so intuitive, but it turns out from a science perspective, from an economics perspective, it's very hard to reason about behavior of agents in a first price auction. And it's actually really nice and convenient to try to think about behavior in second price auctions. And we're going to zoom in so you can understand why this is the case. So let's for the sake of the exercise, basically like try to limit this into this category that we call sealed bid auctions. Okay, so the story goes like this: each bidder I privately communicates a bid, BI to the auctioneer in a sealed envelope, if you like. Right? Platforms provide this on the internet these days. So the auctioneer decides who gets the good, if anyone, and then also the auctioneer decides on the selling price. The obvious thing that we already discussed with eBay is that basically, yes, there's an obvious way to implement step 2, which is to decide who gets the good. Basically, I think all of us will agree here that yes, let's give it let's give the good to the highest bidder. But the way we implement number 3 significantly affects bidder behavior. The way we implement basically what's the selling price, okay? And I'll give you an example. So assume that I'm selling this iPad that I'm holding over here. It's not mine. So that's why I can sell it. So assume that I'm selling this iPad that I'm holding over here. But assume that I'm an altruist, okay? In this case means that I'll give you the iPad for free, okay? The only thing I need to figure out is who of you, like which one is the person that actually will get the iPad. Now, I'm inviting you to make your bids. What would you bid?
I might try to bid first.
Okay.
And
I think you want to bid at the end, maybe? Like try to bid at the last. That's why I was reading also like about eBay and the auction stuff, and there's some people that are really experts in the subject. They were like, you should try to bid at the last, because there's a time normally.
Right.
Yeah.
For both of these cases, basically, I think that would make sense if the last bidder wins, right? Either if you have a time window and the last bidder wins, right? Or if potentially you can only bid increasing prices, right? So you can only say that, like, hey, I'm going to bid like something additional to what's the current lead somehow, right? So the free approach is interesting. You know, that would be more of a differentiating factor. It's like, hey, I'm not going to bid anything. Do you want to give it to me? Try
yeah, bid low.
Okay.
I'm just kind of guessing. But
Yeah.
if I know you're an altruist, and then you're like, it's uncle, you know, it's my uncle, like, it's his old iPod. And you're like, I'll give you $1.
Right.
Right?
Makes sense.
Is it like this? It's like the sealed one you were talking about?
Yes, it's a sealed one. I'm asking you name your price, but you all know that actually in the end, I'm going to give it to you for free.
But what do you want?
It's a great question. I want to give, like, basically, I want to give the good to the person that wants it the most.
I bid the maximum price that I'm willing to pay for that thing.
Okay.
I bid that.
Cool. So most of the, like, basically most of the answers that you actually get on this exercise is people bidding surreal numbers. So basically what people do is they say, like, I'm going to call the price the biggest number that I can write down, you know, basically assuming that I'm not going to have to pay that anyways, right? So people are like, I'm not going to have to pay this number, so like, let me actually, it's probably the most likely that this person doesn't know all of us, like in person. So what I'm going to do is I'm just going to write this massive number, trying to communicate through that basically this is my desire for the good, right? And you will only be able to do this simply because you know that I would give you the good for free, so you don't have to pay the amount. So you can actually go write like 5,067 euros, you know, and this is how most people behave in this. Now, moving to same story, but basically asking you to bid on a first price auction, where basically you would have to pay what you bid. Probably what you would end up doing there is what Abby was doing before, which is you pretty much try to observe what everyone else is doing and then like bid after them, or like try to bid last minute, like try to basically be the person that tries to beat the competition. While this appears to be easy, in practice this is very, very complicated. And maybe Abby, you can also say that it wasn't that easy. But in practice, actually playing, like try to reason about your behavior in the first bid auction is very, very complicated. Because what you really try to do is you try to analyze everyone else's bid. You try to say like, hey, I see this group, they don't really like iPads. You know, like I think that the most that they would have to, the most that they would be actually really, really willing to pay is something very low because they don't like it a lot. So, despite the fact that my true value of an iPad, the way that I value, what I'm willing to pay for an iPad might be 100, I'm actually going to go and bid 50 because that's actually how I perceive the group to behave. Right? So we try to reason about. I think that you think that C things, right? And this is actually already very, very complicated, both from basically from a conceptual standpoint, but also from like basically doing the marketing standpoint. Does that make sense until now? Now, moving towards second price auctions and why we like them a lot. So, as I mentioned, it turns out to be that first price auctions are very difficult to reason about, and second price auctions basically were invented by this guy Vickrey, very famous economist. So as I mentioned before, the applications of mechanism design and the applications of auctions are actually very wide. It's not just about markets, actually. It's about public goods as well many times, right? So this was a problem that a lot of economists have been obsessing with, as it has massive implications on the way that our societies are actually run today. Try to figure out the best possible way to actually distribute a good or a set of goods to a set of actors. So Vickrey spent a lot of time actually thinking about this and came up with this Vickrey auction. So what we want to do here is basically we want to go through the process of like try to do is they have a valuation. Usually, like probably Abby already had a valuation that either consciously or subconsciously she knew roughly what she was willing to bid. Right? Like she knew that this is the upper limit that I'm willing to bid. And usually it comes basically from your own valuation for the good. So we will assume that each agent actually has a valuation. And also we will assume that players try to maximize their utility. Okay, and that's an important concept. So, and utility in this case is defined as the value that you get from the good, right, minus the cost that actually you had to pay for getting the good. Okay, cool. Now we're going to do a little bit of whiteboarding on the iPad. Let me actually. Yes. So before we jump to the whiteboarding, maybe one more slide. So for a given bid profile B, right? So there's a player I, and if they win, they have a utility. As we said, on the first price auction, their utility is VI, which is the valuation that they have for the item minus what they bid, right? The cost that they have to actually get into that item. Very clear. But on the second price auction, basically we have their valuation, which is VI, minus, and there's a little typo here, minus the max that every other agent in the system paid, right? So that's the second highest bid, assuming that the highest bid, and that's why they got the item. Now, if they lose, obviously they have a utility of 0. They don't get the item, so they don't get any utility out of getting the item. Okay? This little tree is important. Does everyone understand that? Is everyone following? So valuations. So we have agents. I see Angie being like so and so. Let's go slowly.
Essentially, yes. Like the figure being kind of.
Let's play together, okay? So basically, we have a bunch of agents, right? We have n agents, okay? I'm agent I, you're agent J, okay? And each of us basically are bidding for getting this good. Now, each of us has a valuation for this good, okay? And the valuation is basically this VI, which is basically I get value. Worth of, if you want to quantify it in terms of money, we can quantify it in terms of money, and we can say I got value worth of 500 euros from an iPad, right? And I'm bidding something for this iPad. Because I read the room, it's a first price auction, I read the room and basically like, oh, it's people are not willing to bid high, I'm just gonna basically bid low.
Right.
Despite the fact that my true valuation of the good is 500 euros, right? I'm actually going to go and bid something low, right? So the utility eventually that I get is my true valuation, which is 500 euros, right? Minus the bid that I had, that I made in order to get the good. Let's assume that the auction was settled at 200 euros. Then if it was a first price auction, the utility that you get yourself, like, would be 500 minus 200, right? So you would have a utility of 300. Now collectively, the total utility that we will all have will also be 300 because no one else gets the good, right? So everyone else has 0, right? So that's by the way the social surplus that we mentioned before. It's our collective utility. Yes? Great. Okay, that's a first price auction. Now in the second price auction, yes?
Can you just walk through without the typo? What is the?
So it's basically the max. It's like minus I basically. Like so, it's basically the max. So the valuation that the agent has still that doesn't change. Minus basically minus basically the second. Think of it like that. The second biggest price that we observed. So we don't know. Like it's another agent. It's not I.
Right.
So
The max that I'm willing to pay.
Exactly. So it's an agent J. Let's say that the agent J was the second highest bidder.
Right.
I bid 100. Right. So in that case, basically like the second bid. Right. So it's another agent that had the second highest price.
Got it.
Right. So it's J not being
Yep.
I. Right.
Got it.
Yeah. Cool. So in that scenario, maybe let's play this. So you bid 200. I bid 100. You bid 200, I bid 100, and the rest of the class. Now, what we're going to do to try to prove that victory auctions are actually quite nice, what we want to do is we need to show, okay, the claim we make is, our claim, is we need to show that I's utility is maximized by bidding VI. So think of it like this, like the world will be actually much more simple if we were all bidding our true value, right? So we want to design a system that pretty much like forces everyone to say, hey, I don't need to think about this. I know that my optimal strategy over here is to bid my true value. That's a property that actually we really like, and we wish that actually our design was satisfying. Okay, let me get a little bit more. So now what we're going to do is we're basically going to fix I. So we say assume that basically agents and assume their valuations and assume other bids. So we're not going to reason. We're going to say, okay, basically you have your own bids. I don't know them. So I'm going to forget them. I'm going to say, like, I cannot reason about this. I don't know what you're going to bid. So take this and fix all of these things. Then let's actually call B is the maximum bid by any other agent except of me, right? So basically B is the maximum bid that any other agent except of me has given for this good. Think of it like actually as max bid by competitors. Let's call them competitors. Okay, it doesn't mean much. And this is the area, by the way, where notation it might help. Competitors of I, right? So I'm I, and competitors of I. So now there are two scenarios here. So the one scenario is that my bid, BI, okay, is smaller than the maximum bid of everyone else. And in that case, I lose, I loses. And as a result, has a utility of 0 that we saw already over here. Yep? Okay, everyone's good. Now there's another scenario, which is that actually my bid is bigger than the maximum of the rest of the class, and in that situation I wins. And basically my utility is the one that we described above. Now, the interesting thing here is that basically you see that my utility is VI minus B, right? And B again is basically the maximum bid except of mine. So it's the second one. Think of it like that. So my utility is basically my valuation minus basically the second bid, because the second bid is what I have to pay in the end. It's the 100, not the 200, to use the example that we have. Now, there are two cases following that. So case one. Now, if VI, which is my valuation, is actually smaller than the maximum bid, except of mine, then UI equals 0. Now, yes, okay, you get it, right? Like, okay, I lost, so then I didn't have any utility. Now, the interesting thing here is that actually that's the optimal thing for me to do is indeed to bid my maximum value, right? Is bid my real value. I still lose, I still get 0, but that's also the optimal thing, right? Think about it, like think about the situation that I described before. She goes into this whole like, I'm gonna chase the price, chase the price, chase the price. At some point it crosses the price that she's willing to pay, and then says that basically, okay, I'm just not gonna bid anymore, right? So she would have actually, if the system was following a second price auction, she would have bid here price from the beginning, here 2 valuation, and then if that wasn't enough, she would have ended up in the same place. So it's already the optimal strategy actually to try to bid your value if your valuation is smaller than the maximum bid. Now case 2, which is what concludes our proof, is the second case. Now assume that basically my valuation is slightly bigger than, or like slightly or like more bigger than the maximum bid from the rest of the class, then the maximum utility that I get is VI, which is my valuation, minus PJ, right? Which is achieved actually by setting VI equals VI, which is my true valuation. And pretty much that settles the proof. Now I know that math is not, basically not everyone is basically on the same level, but try to actually reason logically about what you observed, like participating in a second price auction. What you will really quickly realize that basically it's your best strategy any point in time. We call this actually a dominant strategy in game theory. We say that you have a dominant strategy, which is a strategy that you want to pursue every single time, independent of what everyone else is doing in a second price auction, which is actually to bid your true value. And that's an extremely powerful property that the system has. Okay, and we just proved it following very, very simple math.
Your true value being what you're willing to pay?
Your true value being how you actually value the thing.
So
Yeah.
the true value being the cost of the item, like in actuality.
No, think of it more like the true value being like your valuation of like basically like how much value you get from that. Like I would say that the shoes like worth to me this amount, right? So let's say that this is worth 100 for you. If you find them at the market for 20, you're gonna buy them because your true valuation is 100. You really think that this actually is something that gives you happiness, or however you want to think about clothes, or in this way, or potentially you can go and resell it to the market for 100 because the market actually perceives it as 100, right? So your true valuation is how you value the good, not what you pay. What you pay is basically like your bid, right? Like and in a first price auction, or what you pay is basically the second bid in a second price auction.
Can we use the iPad as an example?
Yes, let's do that.
So you were saying that the iPad is €500. That's the valuation of the iPad.
My valuation of the good.
By the seller. So the seller has valued the iPad at 500.
By the bidder. So are you selling the iPad? Or
Oh no, you're selling it. Sorry.
Okay, so if I'm selling it, it's basically like you need to. The 500 was what you were valuing.
Okay, because I thought that the value of the iPad is €500, and then it's up for auction. So as a bidder, if you're selling it, right, and I'm bidding,
Right.
I know that I can get an iPad at least normally for €500. Right?
No, I think I confused you somewhere actually, which is the part that confused you is that we start an auction and there's no floor, there's no minimum basically.
Sure.
So the summary basically says that like, hey, let the market decide what they want to pay for this iPad, and then each of us now start to reason about what am I willing to pay for this iPad. That's my valuation on the personal level, but each of us has our own valuation for the good, right? So you might say that like, hey, for me an iPad worth $100, and I'm willing to pay $100 for this, and I'm saying that like, oh, actually for me, like I use that work as well, so I might be willing to pay more. So its valuation for me is higher. So one valuation could be 100 for you, mine could be 200, Andrew's could be 300, etc. Right? So each agent has its own valuation for the good that's
and that's
made.
VI.
That's VI. That's right.
And so capital B is what?
Capital, we think of it like that. So we basically all bid it for the good. Okay. So we all wrote on an envelope what we're willing to pay. We sent it to the person who was actually selling that. And now basically this person actually is now ranking all of the offers, all of the bids. Now the B is basically the B is the second. The B is basically the maximum bid except of yours. So you bid something, right? B is basically the highest bid from the rest of the class. You're one agent now observing what everyone else did. And you try to reason about, okay, what should I bid?
So is B a set? Or is B, no, it's one number?
B, like in the iPad example, defaults to a number, right? Which is the maximum from basically the rest of the class. Exclude your own bid, and now B is the maximum from everyone else.
Gotcha.
And it's not a sum, right? It's just like the...
No, it's it's a bid. Yeah. So think of it like that, right? So I'm reasoning about this use case. So I'm willing to pay 100 for an iPad, so I make a bid of 100, and then when eventually we have all the bids from everyone, basically I realized that the second highest, or basically the highest of the rest, think of it like that, the highest of the rest was 75 and came from Amazon, right? So now B got 75, right? So it's the maximum basically from all of my competitors. What was the highest bid that my competitors bid? Think of it like that.
Isn't there a case where VI is the same as capital B?
Yes, it could happen as well.
Yeah, but
How do you settle that?
yeah.
So usually, like basically, you try to engineer a few additional things. So you might try to create increments. So eBay, for example, you wouldn't actually pay the exact second bid, but you would pay like a tiny increment above that, right? So you can try to engineer small things to differentiate between the case that you mentioned. If we have two actors that actually they both bidding the same thing, right? So my bid is also equals to B. So there's no way to settle that between the two. Like we can try to engineer a few things to try to settle that scenario. Yeah. Still with me? Yes, okay. Give me a second. So what we just basically discussed and what we concluded is that we proved this really nice property over here, that in a second price auction the dominant strategy is always to bid your true value, and that's what maximizes your utility, right? So that's the first thing that we proved, and this is quite of an important claim, because no matter what everyone else is doing, you basically know that on the one side you can play the game. It's the easiest way for you to play a game where you know that, hey, actually, like, I should be bidding my true value, and that will maximize my utility. And also on the designer side, we also proved that this mechanism actually maximizes the surplus, right? By very quickly, like if you have the one property, you get the other one. So you practically give the good to the person that wanted the most, that's also paying what they were willing to pay for that, right? So that's actually quite strong. And moving back to my presentation. So,
quick question.
yes.
Why does the auction designer choose to do one or the other?
What do you mean?
Why would they want to have this second auction?
Oh, great question.
Because they would get less money.
So that's a fantastic question, actually. So take the case for eBay, right? So eBay might say that, like, one approach that eBay could take is that we're going to follow the first price auction. We think that actually it leads to worst outcomes for our players, but potentially it might maximize our revenues. Right? That's analysis. So potentially eBay might do their analysis and they have their own objectives. Right? So the platform might have their own objectives. Mm-hmm. So they might say that actually, despite the fact that we know from basically economic research that the second price auction actually has the super nice properties, basically maximizes the utility for players and the designer, we might actually decide to go for something else because it might give us a short-term benefit. Like it might lead to addictive behavior. Think about Facebook optimization problems, right? Like what platforms decide to do, it's not always black or white, simply because many times there's a temporal component, which is you might be optimizing to capture a lot more value in the short term, but not in the long term, etc. My claim is that basically eBay was following the victory auction for many years. I think it was the first 10 years of the platform they were following the exact auction, which was the right strategy, simply because in the end, if you're a platform, you want to make sure that you caring for both buyers and sellers, right? In the end, basically, if you satisfy buyers and sellers, probably you will be successful in the long run, right? In the short run, that's not always the case, but in the long run, that's the case. So eBay, when they were designing a system, they were trying to figure out, okay, what's the best way for us to allocate goods between buyers and sellers that satisfies both sides, right? So that's the important component. Maybe drawing an analogy again, think about something that you might be able to feel better. Think about, again, students and universities, right? So graduates and universities, right? So you want a system that ideally tries to allocate each student to the institution of their choice, right? So you have, like, basically mechanism design helps you make these decisions and helps you come up with solutions that now you can go and compare. The same way that we just compare a second price auction with the first price auction and reason about what does this do to the agents, right? Like what does this do for the buyers and for the sellers, etc. Now, similar story, for example, in this matchmaking, what does this do for the universities? What does this do for the students?
But so in the instance of eBay,
Yes.
it is incentivized to
Make
keep
money.
people on the platform.
That's right.
So whereas universities, that's like a time-sensitive, like short-term relationship, essentially.
You might think about this as the university, but the system designer usually is probably like the policymaker, right? And the policymaker has to come up with a policy, and probably like they operate on the hypothesis that 4 years or 5 years, depending on the term, in the end of the term, they will be evaluated. If they come up with a system that actually is really gross, and I can tell you a lot of gross systems and stories from where I come from. Then they might, at the end of the term, actually be evaluated negatively and lose their, their position, etc. Right? So each system has its own feedback loops. You just need to understand what are these, and then you also need to understand the intervals, like how quickly do they go, right? Yeah. Okay, still with me? Okay, great. So now, summarizing a little bit what we just discussed intuitively. So what we really like from victory auctions, what makes victory auctions awesome, is the fact that they have three properties. The first property is what we call, they have strong incentive guarantees. So, and the scientific term for that is dominant strategy incentive compatible. So in a second price auction, every bidder has a dominant strategy, so they need to set their bid equal to the private valuation for the good, and that strategy maximizes the utility of the bidder no matter what everyone else does, okay? And that's quite powerful. In a second price auction also, another way to think about it is that every truth-telling bidder is guaranteed non-negative utility. You're not going to lose money, right? Like meaning lose money in this case, you're not going to basically have you're not going to have negative utility, right? So you're not going to find yourself in a frustrating situation where you were valuing this 400 and then eventually you paid like a lot more by that. And the system pretty much guarantees that, right? Which is counterintuitive but fascinating. So that's the first component. So strong incentive guarantees makes this auction great. The second thing is what we talked about is also we have strong system performance guarantees. So if bidders report truthfully, then the auction maximizes the social surplus. Think of them as all the sum of the utilities that we played before. And again, the sum of the utilities of all the utilities in a single item auction is pretty much the utility of the person that wins, because everyone's utility is zero because they don't get the good, right? But we just proved with the victory auction that the victory auction actually guarantees that we're maximizing the utility for the social surplus, and that's extremely powerful. You're gonna really struggle to find a lot of mechanisms that actually satisfy that. And then the third thing, which is more interesting for computer scientists, is that is what we call computational efficiency. So this auction actually can be implemented easily. It's not just a theoretical concept, think of it like that, but we can put it in code and have a system that actually operates as expected, right? And especially for computer science, that's something that's many times desired. And we're talking about time usually, like I'm thinking of algorithmic complexity. I'm not going to go there today, but yeah, think of it, this is implementable. So great outcomes, like right incentives, great outcomes for the winner and the system as a whole, and implementable. These are the three properties that we want from every design that we make. Yes?
It's interesting that you talked that in terms of computational efficiency, but it's also about the implementation is like how raw is simple enough that people can actually understand it, right? In order to bid at a true value, it's maximizing their utilities. They need to understand the role. It's also like a booking.
Yeah, that's a fantastic point. So in general, in reality, when you're designing a system, you have multiple objectives. It's never just like black or white, like one thing. Actually, sometimes in the markets, you find like very black or white things, surprisingly, that like, hey, like, okay, maximizing revenues and that's it, right? But usually, like, proper system designers, they have multiple objectives. One time, like one objective that many times we have with algorithms that we come up with is how intuitive they are, how well understood they can be. And the line of thinking there is that basically you might have an algorithm that it's fantastic, but no one understands, so it's kind of a black box. And because I don't understand, I hear that's great, but I'm not going to participate in it, right? So do we have anyone here that does more work on machine learning or has an interest in machine learning, artificial intelligence, all of that?
I had one experience 2 months ago.
Great.
So it's very fresh, and it was my first experience, so I had to like learn a bunch of stuff that I had no idea.
No stress. Like, this is not like showing off or anything like that. So one interesting thing why I'm mentioning machine learning and artificial intelligence, simply because one of the challenges that we face right now with machine learning and artificial intelligence is that we basically have this class of algorithms that you will find them under like the deep learning name, if you heard that buzzword around. So there's this new set of algorithms, they're not that new. Like neural nets and deep learning, all of that have been around for years, but they're getting actually quite a lot of traction in the last few years. One of the problems that we have with these algorithms is that they are black boxes, means that even the designer can tweak them and evolve them, but actually cannot struggle really to reason about what the algorithm really does, right? And that poses a lot of questions around ethics, around you get a lot of different challenges, which I think is where you're going with your question. Yeah.
It feels like a bit separate because here we are talking about rule sets that you're participating. Like there's also many like voting systems that could be achieves a good outcome, but very complicated. So it's not implementable in reality. So it's So I think I was talking about more of that. It's like deep learning feels like it's more done inside of the like a computational part. So it's not much about human understanding.
Right, like a lot of deep learning algorithms are computationally efficient, but they're not intuitive for humans, or like not, they're black box for humans, right? You were talking about situations where the rule setting is complicated, but they are implementable or non-implementable. I don't know.
I think that in the mechanism design, that's definitely the important point, that it's understandable to the actors.
Yes, I would again say depending on the application. So there are certain, like, there are certain situations where, especially in a lot of critical systems, the most important thing is that it works. You know, like in certain critical systems, it's extremely important that it works, and that might come with the cost of like explaining. So it might remain a science thing that a bunch of scientists understand, but the rest of the components that are affected by it don't, and that might be more acceptable there. But in most systems, it's exactly what you're describing, which is ideally you want to make it that everyone understands, right? That's a desired property, I would say. Yeah.
Yes, I need to ask you about what are the examples of complicated things that people don't need to understand. But it will be like after. I don't take too much time.
Sounds good. We can discuss that. Cool. Okay. So just to close the loop with auctions. We went through like a whole story, like trying to figure out where we're coming from, where we're going, right? So we started with sports and badminton, and a very clear, simple case of basically how even very simple things can go wrong and create very confusing incentives. Then actually we talked a little bit about what we, how we think about mechanism design, what mechanism design is versus game theory, right? The two sides of the coin. We talked about very basic, simple questions about try to reason about the agents that play the game, the different actors that you have in there, their strategies, their objectives, the information that they have. And then actually we looked at a real example of auctions. And we looked at a single item auction. And we learned about the victory auction that has these very, very nice properties. Now, I showed you these properties from the victory auction because what a lot of designers do is actually they look for the exact same properties everywhere, right? So like every time we try to make a system, we try to say, okay, the system needs to be incentive compatible. What we say, ideally, each player needs to have a strong dominant strategy that they want to play every time. It maximizes the collective utility, etc., and is implementable, right? But in practice, actually, as you've already figured, things are complicated. This is just the starting point. And I want to have a slide on what makes things hard. So even taking something like auctions, what makes things hard is that we actually have to make two decisions. The choice, on the one side, we have to decide the choice of who wins what, and then obviously the choice of what we have to pay. Even in the exercise in the room, you saw very quickly that probably you felt that like, oh, figuring out who wins is actually easy many times, but actually figuring out what they have to pay is very, very complicated, right? So that's one area that makes things hard. And then on top of this, we have many times information is the most complicated thing. Try to reason under uncertainty, try to reason under like reduced information or varying information within a game. And then to make it even more complicated, you have situations where a lot of actors collude with each other. So in the cryptocurrency space, we find this a lot, and we talk a lot about collusion. So imagine a situation where some of you have already coordinated on how you want to bid, because the good was of extremely importance to you, right? So imagine like try again to come up with mechanisms that capture that. Gets very, very complicated, but also that's where it fun is. And it only gets harder. So I'm gonna pause here. Any questions on this first part, and we're gonna break after this. Any thoughts, any ideas? Just should we hear out the room?
I'm looking forward to applying this. Like, why are we discussing this?
Great.
Well, actually, I had a question on the second price option.
Great.
Like, which, again, thinking about my experiences with eBay, I was wondering whether second price auction actually, say, pushes the valuation or like individual valuation, like, up for knowing that ultimately you're going to pay the second price. So, in the case of the iPad, for instance, if my true valuation is 500, but my guess is no, is that, I don't know, someone else may get close to that, then I bid, I don't know, 550 or something.
Yeah.
Is that, I mean, I guess, yeah, I don't know, is that also a property of the, like...
Can you repeat the question?
Yes. So the question, the way I understand the question is that basically you were wondering if, in the case of eBay, if basically this whole idea of the second price auction eventually makes you bid more, right? So the answer is no, it doesn't, right? So like again, assuming rational agents, it doesn't. But I think what you're hinting and what we saw earlier with Abby, it was the same behavior that I had like previously on auctions, is that there's a behavioral component as well, right? Many times you go in an auction, you just want to win the thing. You know, you forget completely, like, fuck the science. Like, I just want to get the thing, I'm willing to pay whatever, right? And at the end of the day, when the emotions are a little bit calmer, you go home and you're like, whoop, I fucked up. You know, that doesn't make any sense. Like, why the hell did I pay for this thing? So in economics, you know, there's a behavioral component that comes in the way, like, you know, there's the whole thinking about rational agents, but many times you would argue we're not rational, right? So there's that, and there are certain platforms that I guess they try to gamify the process and get you to bid as much as possible. So you might see that, but again, try to reason more, like, you know, from a theoretical standpoint about some of these auctions. No, in this use case, in this case that you mentioned, if you had bid above your valuation, there's still a high likelihood that actually you win the good, right? Like, so, and in that case, like, if everyone was doing that, potentially you might have ended up paying like more than what you wanted to pay, and then you might have negative utility, right? So again, like as we saw with the proof, actually, like if you, and I'll certainly note after, if you go through the proofs, you will very quickly realize that, oh, this is what is expected for me to do here, independent of what everyone else does. Yeah. But great question. I think it opened up another. Any other questions? Any thoughts? Does this make any sense? Or do you see any applications that come to mind when you use, after the things you heard? Anything that comes like? Okay. All good. Great. So I'm gonna pause here. What time is it?
Good question.
So it's actually 8. So we've already done an hour and a half. Interesting. So I'm gonna pause here. Maybe we'll do a 5-minute break, and then we can talk a little bit after about cryptocurrencies and some of the applications we can design there, and we're gonna keep it in use. Yeah. Cool. Okay. 5-minute break.
Yeah.
Yes. Great. How familiar are you with cryptocurrencies? Everyone heard of Bitcoin, I assume, right? How should we go around maybe quickly and say, hey, do you understand how Bitcoin works? What's the deal about it? You can say yes, a bit, no. No, like no saying. There's no like, don't need to know anything. I see some face being like so and so. So and so.
I mean, I read a white paper a year ago.
Okay. Okay.
How much is
That's a start. That's a start. That sounds great. Okay. So primarily, so maybe talking a bit about Bitcoin. This is not a session about Bitcoin. You're going to have like a few sessions on cryptocurrencies, smart contracts. This is not the goal of the day, but just trying to say how all of these things connect the dots. So a lot of cryptographers for many years they were trying to develop internet money. Okay, so this is not a new thing. This is something that a lot of different hackers have been trying to do over the years. A lot of people were trying to actually develop peer-to-peer money, right? And a lot of these people have their own political reasons for that, but the main reason was coming basically because of disbelief in banks or governments. So a lot of these people were skeptical about that, and they wanted to try to create sovereign money, as they call the money that actually is not controlled by the government. Again, leaving the politics aside, a lot of people have been trying this for years, but they would never succeed on that. And the problem that you have there is that, again, it's a problem of mechanism design primarily, cryptography and mechanism design. And the problem goes like this: that imagine we have a group like this, like we are 10, 15 people that actually want to have our own currency and transacting between us. The problem that we have is that without a trusted intermediary, it's very hard for us to coordinate, right? Meaning that assume that we all come up with, our own little currency, we create, paper money, that they all, worth one, call it like P2P coin, however you want to call it, right? And now you start transacting, and because we're transacting, ideally you want to keep track of basically this money flow. And in order to keep track of its money flow in a peer-to-peer setting, that's very, very complicated. It's another mechanism design problem, right? Which how can this whole system actually be trustworthy without us having to trust basically our money issuance or control to one party, right? So it's again trying to connect the previous part. It's a problem of incentives in many cases. Eventually, the Bitcoin white paper came out and this problem was solved, and the primary innovation that the paper brought was an innovation in mechanism design. That's the only point that I'm trying to score here, is that if in the next few months or years you end up being more involved in, specifically in the cryptocurrency space, which is a sub space from the overall broader peer-to-peer centralized space, then I highly recommend that you actually try to understand Bitcoin from a mechanism design point of view, from an incentives point of view. So because of that connection, between cryptocurrencies and mechanism design, basically we start seeing loads of applications right now of some of these things, and we call this area of research now, some people start calling it cryptoeconomics, because it combines cryptography and economics, specifically the branch of economics that it uses is mechanism design and game theory. And the way to think about this is that basically some of the systems start to use cryptography to prove properties about things that happened in the past and were recorded. A very simple example is, I'm sending Abby 10 coins. I want this to be recorded, that it's me sending to Abby these 10 coins to keep our accounting right? So in order to do so, we use cryptography. So now, this is just one case, but try to abstract from that, think about a set of properties that we can prove about what has happened in the past. Many times you will see us basically using digital signatures, right? So you're going to hear more about cryptography in the next few weeks. But what I want you to remember is that primarily we use cryptography to prove properties about the past, about what happened, and make sure that these things are actually recorded recorded somewhere. So that's where we use cryptography, and that's the crypto part. And where we use economic incentive is for ensuring that these desired properties hold in the future, right? And that's an important distinction. So cryptography for all the things that happened in the past, and the combination of cryptography and economics to make sure that we'll actually be able to enjoy some of these properties in the future. Again, try to think about the example that I talked before about us issuing our own currency. We need to come up with a system that we come up with solid incentives that basically the person or the system as a whole is not rigged. Because if it is rigged, then potentially we cannot trust the system anymore, we cannot trust our money to that thing and use it anymore. And we use economic incentives for that and mechanisms. Now, try to bridge the gap between some of the things that we talked about before, about auctions and some of these things that actually are slightly different on the crypto economic space. We have the following. So by design, a lot of these crypto economic systems don't assume the eBay that acts as the market maker that basically connects buyers and sellers and actually also settles disputes many times between them, right? So you don't have this one trusted actor that if shit goes wrong, you can at least go and negotiate and try to figure out how to resolve this, right? So many of the systems by design remove that actor from the mix because usually trust goes both ways, right? Like I can trust you and that's great because I can use you, I can basically use you to resolve a conflict, but also because I trust you, many times I give you powers. So it's all about the balance about these two things, right? There's a question, yes? Oh no, okay.
I'm servicing.
Okay, sounds good. Yes, so what's different in crypto economic research basically is that many times we don't have the center and control of these games. The platform is many times just a piece of code that we deploy on the internet and then it works, right? And because we deploy on the internet, many times actually it's very hard to shut it down, right? Like almost impossible to shut it down. So that again, from a designer point of view, makes it much more complicated. You need to design the system, get it out there, and this thing in the open needs to work, right? So that's the first thing. The second thing is that basically because we're using cryptography, we have anonymity everywhere. And while this doesn't appear to make a big difference when you start to engineer systems, it actually does because many times when we engineer systems, the fact that our identity is connected somehow basically gives us a bunch of options of last resort. So, for example, take the situation that happened on the badminton case. What happened after basically this whole thing? The referees, as you saw, basically banned the first team. They settled the game, and then basically the badminton institution, I don't know what is their name, they eventually banned both teams. They came in and said like, hey, we know who you are. Actually, what you did there wasn't nice, so you're all out. So they were able to do this because they knew who people are, had identity, and they were able to use that identity to say, I know who you are, I'm going to penalize you for certain of your behaviors. On crypto economics, actually, we don't have that because everyone is hidden behind the key. And many times, actually, a person might be hidden behind two keys or n keys, right? So we don't have this notion of identity that is great many times for privacy-preserving technologies, but also is very challenging when you are a designer of a system. So that also changes a little bit the game. We talked about dispute resolution, so as of now we have very limited dispute resolution in some of these systems. So the norm right now in this space is what we call immutability. Basically, you just, you have the state of things, and the state of things is the state of things. There's no negotiation around it. Right? There are solutions right now where people basically try to design systems for that, and there's a reason for that, which is like take the case of eBay. If we want to build a decentralized eBay without the company in the middle, potentially you need its basic user experience. You need to have some kind of way to solve dispute resolutions. Think of the case of a decentralized Airbnb, for example. If we had a platform like this, again, you want your users. You want to operate on the assumption that disputes will emerge, and you don't want to default into, oh, they emerged. It doesn't matter. You want to provide, again, a good user experience, right? And when you have centralized actor, basically, the centralized actor does a lot of that job for you. So Airbnb many times tries to settle issues between oh, the house wasn't clean, I'm not paying the price, right? How do you do this in a decentralized system is actually slightly different, and it's actually much more complicated. So these are the things that make some of these systems that you will be seeing in the next few weeks much more complicated from an incentive point of view. What I wanted to do for the last part was actually to play a game with all of you on and come up with a game with all of you, but we have actually only 10 minutes. We spent quite a lot of time on the first part. So what I'm going to do is basically I'm just going to talk a little bit about the game, show you some things, and then for the ones that are interested, leave you with the exercise that you can follow up if you want. Yes?
Before moving on, can you go back to the last slide?
Yes, absolutely.
So when you're talking about cryptocurrency or crypto economics, it's a technology is blockchain.
Yes. So the way that the technology is manifesting today, yes, it uses like.
And you can change it after, like once you implement and deploy it, you can change it. Like that's how it works.
Right. So most of this, basically, most of the way that these networks operate today, you like when something is recorded and it's there. Yeah.
But that sounds like whatever you design it, you're very much stuck with it. What are the things that can you change, like in terms of economic incentives? If you see something that doesn't go as you design, or if you see something that's like harming the economy, then how can you change it?
How can you improve upon it, right? So that's a great question. So there are two things, and again, I want to make sure that I don't confuse you with both of them. So there's the agent side, and then there's the designer side, right? So you can think of yourself as you participating in an economy, in the Ethereum economy or the Bitcoin economy, right? So the transactions that you have in that economy are recorded, right? They are recorded and associated with a key. The internet doesn't know that this is you particularly that is transacting, but all of these things are actually recorded and are actually recorded there permanently, right? So this is the whole concept of immutability. For certain things, this is desired. Like if you think about what Bitcoin is, primarily an accounting system, right? So it's a ledger that we all write down. I send you this and you send me that, and we printed this, etc. Right? So actually, you want this immutability, right? From a system design. Now, we talked about agents transacting and all of these things being recorded. Now, also, although the point I'm bringing up is that, like, oh, if these are economies, think about you are the Ethereum, the person that basically designs the Ethereum economy or the Bitcoin economy. Obviously, you will observe things and you want to be able to change them, right? Like if something is going wrong in your economy, you will be able to change them. But you can do this. You can even do this in decentralized systems. You cannot change like the artifacts. It's very, very difficult for you to change the artifacts, but you can change the policies or some of the rules that you're setting within some of the economies. But because it's a decentralized system, this comes with a cost. And the cost usually is coordination. Because there's not like, the one company that's responsible for the system. Usually the systems are protocols. We deploy them on the internet and they just are there and they work. And now if we want to change them, a significant amount of the participants need to coordinate and say, yes, we want to move forward with that. Right?
So there's a voting system, or how does it work?
It depends. So there are by now, there are literally 2,000, I think, or 3,000 of these systems at scale. Each of them try to basically differentiate, and they follow different approaches in their governance, as we say. So this is pretty much the meta-governance of the system, right? So many of them actually default into no change, minimal change, basically to work. So we're not going to touch it, that's it, and the Bitcoin community is much more closer to that. And then other systems actually are still more open. Many of them basically have informal processes about how to change that, and then there's a group of core developers that actually still have the right to push new code and change the economy. Others actually try to run it more based on plutocracy. So basically they say, if we want to push forward a change for a system, we will have to vote with our money. So because these are economic systems, so many times you see this. Other systems try to default into more democratic, like basically majority voting, but the problem we have is anonymity. So you can
you can just create multiple
exactly. You can game the elections by actually, you don't have this one member, one vote. People on most of these things actually vote with their tokens, right? So you have variations of this whole thing, but the point that I think I want to communicate that's important is that these systems, in comparison to their centralized counterparts, are much harder to change because they involve coordination. That's the price that you have to pay, which is a decentralized system usually involves components, and because there's no leader, there's no one person responsible for the whole oversight, every change needs to go through approach, and many times that's desired. For certain things that actually are very critical, you prefer that. But many other times it isn't. Yeah. Did I answer your question? Okay, cool.
Yes. It's
Cool. Any other questions?
How long does the game take?
So we're not going to do this. Just wanted to maybe show it. We have 4 more minutes. Maybe show it. So yeah, anyone that's interested, actually, you can go read more about it. Or if later in your career, or like as you're exploring the space, you come across that, you know that we have a bunch of resources here that they can help you. Okay. Cool. So I call this the stable going game because the objective of the game. The objective. Yes, the objective of the game, the objective of the designer is to create a new currency. Okay. So the objective that the designer has is to create a new currency that is pegged to another one. What do we mean by pegged? Is basically it has always the value of that other one. One classic example you can think is that we want to create a new currency that we can call it P2P coin, just for the same of the exercise, call it Elecoin there. So that is always basically one Elecoin always worth €1 or $1, right? Now you might be wondering, why the hell do I want to do that? Like, why the fuck should we do this? So I mentioned before that basically like for the last 10 years with the emergence of cryptocurrencies, we now start having internet money. And some of the nice properties that internet money has is that basically we can send it around the world instantly. So basically have some of the properties that code had and information with the internet. So what the internet did for information, this is what cryptocurrencies try to do with value. Right? So they try to basically make value be programmable, very easily send it on the internet. Basically anyone can issue currencies, right? So practically though, this gives you a bunch of nice properties, which is, for example, like I can send money to my parents in Greece, and they can have it, and with very low costs. Like you don't need to be paying like all of these crazy costs that primarily come because of financial institutions that are in the middle, that are oligopolies, that can count whatever they want, right? So I can basically send loads of money with very low cost very quickly. Actually, I think a few weeks ago someone sent $1 billion worth of Bitcoin, and the cost that they paid, I think it was something like 10 euros or something. So something insane. Previously that would be literally hundreds of thousands of euros as cost, right? So now, back to the stablecoin game, one of the problems that cryptocurrencies had until now was that they're very volatile, right? And we see them go up and they go down, right? And while for certain people and certain use cases that's not a problem, for other people and other use cases that is a problem, right? So for that particular reason, a lot of people on the internet have been obsessed with that problem. Can we create a cryptocurrency that pretty much is always pegged to the dollar? You can actually always redeem it and get back $1, right? And we call this stable coins. Now, one way to engineer this stable coin is the following. So let's say that basically we all over here wanted to issue a new currency. It's offline for now. It's not digital, just for being precise. And one way to do this is basically the following. We can all agree that we're going to make this cryptocurrency, this currency, and how we're going to do this is basically all of you that want to participate in this game, you're going to come to me and give me your dollars or euros, right? So you're going to give me, each of you, one euro, let's play with the euro for now. And then I'm going to basically take this paper, right? And then write down one Elecoin. You're going to give me one euro, I'm going to give you one Elecoin. And now you have the Elecoins, right? And I have your euros. And now I can keep basically your euros as collateral. At any point in time, you can come back to me and basically you can give me back the Elecoin, and I'm going to give you back your euros, right? So sounds pretty fair, right? 1-to-1, simple, great. Now, this is what you see this little diagram over here, where the class gives me basically one, I give them one of these new coins, and now basically you can use the class, you can start transacting with these Ele coins. Assuming that Ele coins were interesting to you, you can now start exchanging goods between you. You can sell your salad or the remainder of your salad for two Ele coins, and then basically, yeah, I can sell my iPad maybe without that option. So this is basically the market. We can now start transacting with this new currency over here. Now, while this thing appears to be fair at first, and in many cases it's fair and okay, it comes with a bunch of problems that actually don't appear immediately to the user. So the one problem is that I have all your money, right? And now you all need to trust me to keep your money, right? So, and I can take the money and run if I want to, right? Like, how are you going to stop me? I have your money, right? And if I take your money and run, then immediately you cannot go back and redeem the Ele coins for dollars. So there's some kind of trust involved over here to this currency, right? Also, additionally, you can imagine a system that if this was a big class and we were talking about thousands of dollars or euros, potentially, like, I don't want to keep this under my bed, so under my mattress. So what I'm going to do is I'm going to go to a bank and basically put my money to the bank for the bank to store it, because I don't want to have that responsibility. But the problem that is being introduced here is that also now the bank might take your money and run, right? And you might think that this doesn't happen, but it has happened, for example, in my country, like 6-7 years ago, where because of the economic crisis, basically bank accounts above the threshold got a haircut, as we call it, right? So these are problems that actually a lot of people have been obsessed with for a while. And there's a third problem that might not appear to be the case, which is again similar in nature, is that for now I do this work. I play this game with all of you, and the issuer, whichever it is, does this work for free pretty much, right? So I'm the issuer, I keep your money, whenever you want to come, you come, I give you back your money, like I do this thing, and I don't make any money myself. Yes?
Yeah, but if you will just make a deposit to the bank, then you'll get the interest for all the money.
Great point. So that's one potential case, right? So this is exactly where I was going, which is basically, for now, I wasn't making any money. So potentially, what I might want to do is, I might want to go put your money in a bank, as we discussed, and now I can potentially take your interest. Great catch. So I might have an income from that. Another way might be that, like, actually we start seeing now negative interest rates, for example, which is more of another topic in the economy. So what I might go do is, actually, I might find an investment opportunity that I like. I'm sitting on a bunch of money, they're not doing anything anyways, so I might actually go and invest them somewhere. But the moment that I invest them, I'm introducing another risk, obviously, right? Like, what if I lose this investment, right? So these are all problems that primarily rely on trust, and mechanism designers and cryptographers have been trying to solve, and like, by now, basically, we have actually really solid decentralized solutions to this problem. And we have cryptocurrencies that basically try to do exactly that. So one cryptocurrency that you might hear in the news recently is called Tether. And the whole concept of Tether is pretty much replace the class with anyone on the internet. Now, like, the issue is this company called Tether, you go and give them basically your dollars, and then they issue this new digital money that they call Tethers, and they claim that basically we're keeping your dollars in the bank, right? Now, this whole thing has gotten that big that basically pretty much, I think, have like something like $1 billion of Tether issued, which means $1 billion somewhere in some kind of bank. And the story, at least, like the news recently, are that basically what Tether did was exactly number 3. They took some of the money, because a lot of money, they actually used the money to invest them, and now pretty much no one knows how much money is there, right? So that's one example of what not to do. And I don't know exactly what happened there, but this is what the word on the streets right now is that there's something funky there. Now, the reason why there's something funky is because incentives don't align, right? Like, think about what we discussed before, like what are the different incentives for the players? If I'm this issuer and you're giving me $1 billion, right, I might do something with. Like, maybe it's actually much more profitable for me to do something with that, and I might actually be able to do this. So that's where especially things at scale start to not work so well. Here you know me, I'm around, if I do bad things, you might come and beat me and take the money. Like, you can do all of these things that, might sound funny, but at scale actually they don't work so well. So incentives don't align. Tether is one example of how this works in a very similar way. You give them money, they put them in a bank account, or they claim that they put them in a bank account. They give you new digital money that now you can use to transact on the internet with all of the nice internet properties, instant like transactions, low fees and all of that, right? But it comes with risks. So another team that actually, and you can see the ledger of the Elecoin, but another team that has been working upon this problem is a team called MakerDAO, that basically they started this journey, I think, back in 2014, and the whole point was like, can we really improve upon the previous design? Is this the only way for us to actually issue an internet native stable coin, a coin that always one coin equals, one of these new digital coins always equals $1, without actually having these risks? And they've been using that kind of design and incentives in order to be able to do so in a decentralized setting. And I'm going to pause here. Like, what I wanted to do is actually work through their design with all of you. So there are a lot of notes here, which if you're interested, I'm more than happy to send to you. But I'm going to pause here. I highly recommend that you look on their system and that you try to reason about what's really going on in there. How are they able to accomplish keeping this new stable coin, the issuing to the dollar without actually having trust involved in the mix, or some, basically, with minimizing trust. I'm going to pause here. That's all for now. Thank you for your time. Thank you.
Ella, do you have some time to, so it is now 8:30?
It is 8:30, and I want to respect people's time. It is 8:38 actually.
So, but you can stick around for a little bit longer?
I can stick around and we can do questions if you want.
Okay. But anyone who has who needs to leave, feel free.
Yes.
That's the rest you'll see of me this week. But we'll see each other on Monday, same place, same time. And just wanted to mention a couple other things. I hope the person who left their scarf got their scarf. And also Keybase. Sign up for our Keybase team. It's going to be great. Ella is going to share all of this material on there. And it's where we're really going to start getting a lot of material from the lectures, additional resources to help you dig in deeper, and hopefully additional conversation between you all, between you and some of the lecturers like Ellen. So we're going to get a lot more comfortable next week, so I will start calling people out who don't speak. And then I think that's it. One more shout out, because Emily brought it up today. I am looking for people to write blog post summaries of these lectures. So if either Stakos or Eliz really interested you and you want to dive, you want to summarize the material, it will help you to reinforce your learning. And I'm happy to assist in writing it, but it will provide a great chance for you to start creating your internet footprint in this space. And Elu will certainly review any blog posts before it goes up.
Yeah, that's the same for every other lecturer. I think if you are interested in writing something, we can definitely contribute to share material, co-write and stuff.
Yeah. So it's a really cool opportunity. So with that those were yes.
But when do you assume those blog posts to be ready?
Yes,
we are. I mean, I have